Actually, in the light of the discussion that we had yesterday, I made some slight modifications, some adjustments, and therefore I would like to repeat somehow and also present some new ideas, some new material that I have just included into the lecture, the things that we have discussed yesterday. So please let me go back some slides before we finished yesterday, which was about the crucial notion of an eigenstate and an eigenvalue. So what we have learned yesterday was that the complex number solving the eigenvalue equation, where A stands for an operator, so a homomorphism in a Hilbert space, acting on a Hilbert space vector, which was written in the direct notation here as a cat symbol. And this reproduces or rescales basically this vector, and it produces the eigenvalue as a scaling vector. So then we were talking about an eigenvalue for an eigenstate of this operator here. And now, of course, we have seen that this eigenvalue equation can be transformed in this equation here, where we have now a linear combination of operators, namely A minus A times the unit operator, the identity matrix, so to say. And then we see that all these eigenvectors are mapped onto 0 by this operator here. So these vectors belong to the kernel of this operator, and this kernel is called the eigenspace of the operator for the particular eigenvalue A. And by the way, what we can see here is that these eigenspaces must not be one-dimensional. In the case that are one-dimensional eigenspaces, we say that these eigenvalues are not degenerated. In other cases, the eigenspaces may have some arbitrary dimension, which always reflects that the eigenvalue here is degenerated, which I haven't mentioned yesterday. So what we have learned yesterday as well is that the eigenvalues of the self-adjoint operators are always real numbers. So they could be used to describe observations. They could be used to describe measurements. And moreover, the eigenvalues of projectors cannot be cannot assume other values than 0 or 1. And now I have introduced or included this slide as well, because this now connects the eigenvalue problem to the observation. So we call the self-adjoint operators over Hilbert space the observables of our system. And that means the measurement of such an operator, such an observable in the eigenstate is given, the measurement value is given simply by the eigenvalue of this corresponding eigenvalue equation. We have been here. And actually, what we have discussed yesterday, I think that was a question by Seraphim about reproducibility. And maybe I will do some calculations on the blackboard as well. So what we have asked yesterday, if we have such an eigenvalue equation, so A applied to the state A reproduces the state A with eigenvalue or with measurement result A. But now let us think about a second operator, which applied to the same state also satisfy an eigenvalue equation. So that might be B as a measurement result of measuring the observable B, but reproducing the state B. What does this mean? So we could apply AB to the state A. And what does this give? So first we have to apply B to the state A. That means getting the eigen, the eigen A, of course. So that should be the same eigenstate. That was the basic assumption here. So this is the same. B to A is B times eigenstate A. And then we apply A, but this is just a scalar. So this commutes with every operator. And this gives B times A. A is the same as AB. These are just real numbers or complex numbers. Real numbers in the case of self-adjoint operators, of course. And then we reproduce the state A. And now we can do the same think the other way around. And you see, we get the same result. And this means essentially that these both operators, they commute. So we can take the difference applied to the state A, and then because here we only have some numbers multiplied by the same vector, this is 0, and therefore we see that AB is the same as BA. And this is the crucial point when we get reproducibility, or when we get non-perturbative measurements in quantum physics. The necessary condition for that is that the operators must commute. It's a crucial point in quantum physics. So it's not everything different like in classical physics. In classical physics, everything commutes with everything else, and therefore all measurements are non-perturbative and all measurements are reproducible. In quantum mechanics, we can have this as well, namely in the case that operators are commuting. Then we have non-perturbative measurements. So then we repeat what we have learned yesterday about the spectrum. So we simply say that the set of all the eigenvalues of one operator is called the spectrum, given by the set where we have the eigenvalue equation for all the different eigenvalues. And then we said that the spectrum, if the spectrum is countable, it's called discrete, and otherwise it's called continuous. And then we saw that this spectral theorem holds. So let A be a self-adjoint operator with discrete spectrum. And then we have an eigenspace decomposition of the entire Hilbert space into the respective eigenspaces of the operators. Then we have seen that the self-adjoint observable here, the self-adjoint operator here, gets this representation that the eigenvalues have to be multiplied by the projectors upon the eigenspaces. And this linear combination has to be computed for all the elements of the spectrum. This was the spectral theorem for discrete operators or discrete spectra. And then we have also learned later in the last lecture how this applies to continuous spectra as well. Well, then I have talked yesterday about measures. That measures are basically mappings from subsets of a basic sets. So mappings from a set algebra, from a Borel algebra, to the non-negative real numbers, so that each set of this subset, each subset of this space gets a number assigned. And we got this simple example for the real numbers, where the Borel algebra is generated by all the closed intervals. We can assign to each closed interval the diameter of the size, the span of the interval, S, which is basically the back measure in this case. So particular measures are called probabilities, namely when they are normalized. So when the measure of the entire base space, so to say the event space, is 1. And then I have explained yesterday that we can define this kind of conditional probability, namely by taking the measure of the intersection of two sets and normalize this by the measure of the second subset here, and this gives us the conditional of A given B. And then I have mentioned yesterday that there is this law of total probability, that the measure of the probability of an event A, or the measure of the set A, becomes the sum of all the conditionalized probabilities A given BI times the measure of BI in the case that the BIs are mutually disjoint and they together cover the entire measure space. But now I have realized also, we have discussed this yesterday, that the proof of this law of total probability depends crucially on the lattice structure of this Borel algebra here. Namely, that Borel algebra must be a Boolean algebra, or must be a Boolean lattice. And therefore, I have looked into my other presentations, and so now the notation becomes a bit different. But this is basically the law for the proof for the law of total probability. So here there are some slight changes. So what is called omega is x in the previous slide, and what is called a bar simply means x minus a, which is a complement set. And then we can see how this proof works. And this PR now simply denotes the measure mu. So the probability of or the measure of a set B is, of course, the probability or the measure of the set B joined with the entire probability space. This is clear, because B is a subset of omega. Then we can replace omega by the union of any set A and its complement. And now here we have to employ the law of distributivity for join and meet. And then we get the probability of B intersection with A and B intersection with A complement. And then, of course, here now we apply the law of sigma additivity. This is the probability of B intersection A plus B intersection A complement. And here you see one part of the Bayesian conditionalization rule. So now we can replace these expressions by the corresponding expressions using conditionalized probabilities. And this is basically the outcome of the law of total probability. So that was my idea to include this slide as well, in order to demonstrate that here we crucially use the distributivity of the underlying lattice, which must be a Boolean lattice, in order to derive this law. And this law is broken in quantum systems when we do not have Boolean lattices anymore. Well, then I talked yesterday about the general notion of an observable, which is just the generalization of the spectral theorem towards continuous spectra. And here the crucial point is now that we have to introduce a new concept, namely a function from a Borel algebra to the operators over a Hilbert space. And we do not allow for any operator, we only select projectors here, and then we call such a mapping a projector valued measure. That means some subset of our underlying measure space, which is the spectrum of the observable here. We assign to each subset of the spectrum a particular projector, which reproduces the measurement that we have a state that belongs to exactly that set or that subspace of the Hilbert space that is described by this projector. And eventually here, this is just a convention to write projector of the infinitesimal closed interval here, because this differential is just the measure of an infinitesimal small closed interval. Well, then just to repeat this as well, we have seen yesterday how can we define so-called linear forms or linear functionals, which are homomorphisms from a vector space into the underlying number field. So to each vector, we associate a complex number, and one particular form of such a mapping is called the trace. The trace of an operator is given by the sum of all the scalar products that A assumes between two states. So A applied to a state n, and then we have to take the corresponding bra vector in order to compute the scalar product. And of course, because we are sometimes dealing with infinite dimensional spaces, we have to interpret the sum as a convergent series, and so therefore trace must be well defined, it must lead to a convergent series, and therefore we talk about only a particular class of operators which have this finite trace, and they are called normal operators or trace class operators. So, and that was what we have discussed yesterday as well. So we can present a complete family of orthogonal projectors such that the sum is the identity operator in the Hilbert space. Then we present some non-negative numbers that altogether sum up to 1. So it's the partition of the unit. And then this linear combination, this complex and this convex linear combination is called the density operator. And then we started yesterday to discuss the principles of quantum theory. So the state of an isolated quantum system is a vector in the Hilbert space, and that vector we call a pure state. Observables are in general the self-adjoint operators on the Hilbert space, mapping states into states. And usually we have this description here that observable or an operator applied to a state psi gives a different state phi, and this means perturbative measurement. And only in the case when the state reproduces here, particularly with a scaling factor, we see that there would be an eigenvalue equation in the non-perturbative case. Then the eigenvectors of any observable supply an orthonormal basis of the Hilbert space, which we can enumerate in that way. And now the pure states are always superposition states of a given basis of eigenvectors of a given orthonormal basis. And so we can write this arbitrary state as a linear combination of our basis states with complex coefficients. These complex coefficients can be computed as the generalized Fourier coefficients by simply computing the scalar product, the projection, basically of the given linear combination onto each of the basis vectors. Of course, scalar products describe geometrically projections. And then measuring the observable A in an arbitrary state psi yields some eigenstate, but only with a particular probability. And these probabilities are given by the square moduli of the Fourier coefficients of the projection magnitudes. So, and now after having measured A, the system is with certainty in one of the eigenstates. And this we have discussed yesterday is, so to say, an assumption that has to be purported into quantum mechanics by this famous projection postulate. It cannot be derived from quantum mechanics at the current state. And this is called the preparation of a state. So in a physical experiment, we would have to prepare a state. And how can we prepare a state? Always by performing a measurement. And then we are sure that after having performed the measurement and measuring an eigenvalue as the measurement result, we can be sure that we are now in an eigenstate. And then you see here in this derivation here, what happens if we apply some observable to an eigenstate. I call it n now, given A or given n. Times n, and if I repeat this, what happens then? Well, the first evaluation gives this commutes, of course, this is just a number. And then we still have the same state. So it is a non-perturbative measurement, but instead of the measurement value n, we get the measurement value L square, because this is simply the operator A square applied to the state. And here you see in quantum mechanics, we all again have that kind of non-perturbative measurement that after preparing a state, we do not leave this state by applying the observable once more. So, and now in the general case, when we do not have eigenstates, we can compute always expectation values. So this brings the connection of quantum physics to statistics, that we have to compute this expectation value depending on the state psi of the observable A, which is simply the scalar product of psi and A applied to psi. Using this new concept of an eigenstate, we are able to define what is called the dispersion. And if you look at this formula, it's simply the formula for computing the statistical variance of some stochastic variable. So we call this the dispersion in the state psi of the observable A is the square root of the expectation value of A square minus the square of the expectation value. And now we can state that eigenstates are always dispersion free. And this we can also prove with a little calculation. Oh, I'm producing a lot of dust. So what does this mean? We have to compute the dispersion for an eigenstate. So that means we compute the expectation value of psi for A square minus the expectation value of psi of A to the square. I can write it this way as well. So what are the expectation values? The expectation value of psi of A is simply psi and psi. And now we have said that psi should be an eigenstate. That means A applied to psi gives some value, I call it A again, and reproducing psi. This is a scalar number. This is A psi psi. And because we are always assuming that our quantum states should be normalized, that should be 1. So the expectation value of the observable A in the state psi simply gives the measurement result A in an eigenstate. And of course, what we have already seen in the computation, in the calculation before, evaluating the expectation value of A square gives A square. Now everything is clear. We have to insert A square here, and we have to insert the square of A, which is A square here. And then you see that the dispersion of A is 0 if the state is an eigenstate. Great. Now, what we have also shown in the calculation before, observables that are not simultaneously and not non-perturbatively measurable, that means basically that these two observables do not commute, they are called complementary. And in the other case, if they commute, So if it does not matter in which order we apply two operators to a given state, they are called compatible. So we have these two distinctions. This distinction, compatibility always means that we can compare observations without any perturbation. And complementarity means that measuring one observable destroys the eigenstates of the other observable that was measured before. And now the formalism of quantum mechanics also allows to estimate the relationship between the dispersions or the variances of complementary observables. And there's also a proof for this famous Heisenberg uncertainty relation. The proof basically uses the Cauchy-Schwarz unequation, which I do not have prepared now, but we can look at this as well if you want. So that means basically that always for two observables A and B, which do not commute, we can derive this relationship for the corresponding dispersions. The dispersion of A in state psi times the dispersion of B in state psi is always larger than 1/2 as a scaling factor, but essentially the expectation value of the difference of AB minus BA. So this expectation value is, so to say, a measure of the perturbation involved by these complementary observables. And if we compute this product of the dispersions for the probably most famous operators in quantum mechanics to momentum and position, we get the Heisenberg uncertainty relation as it was presented first time by Heisenberg, that this is just a multiple of Planck's action. Then, of course, in quantum physics, we have to talk about dynamics. And interestingly, states, namely vectors in such an abstract Hilbert space, evolve deterministically in time according to the so-called Schrödinger equation. So what I have done here is I have introduced an operator K, which is not including the Planck constant here, because it should be the aim of this lecture to present the framework of quantum mechanics independent from particular physical applications, so to say, and therefore it makes sense not to introduce the Planck action constant at that point. But of course, we can express the standard so-called Hamiltonian operator as a multiple of this so-called generator of the time evolution. And then we get this partial differential equation here. And of course, K is a self-adjoint operator related to the so-called Hamiltonian, which governs the deterministic dynamics of systems and quantum. And so now, crucially again, we have two different kinds of evolution. We have a deterministic evolution that is governed by the Schrödinger equation, namely this partial differential equation here. And then always we have this kind of evolution that is given by measurement. So if we measure an observable in a given state, this state is reduced to an eigenstate of the corresponding observable. And this is, of course, non-deterministic. It involves all these probability factors that are represented in the superposition state. And so that was really a great riddle of this so-called pioneer quantum mechanics. How can we relate these two different concepts, deterministic equation on the one hand side and that kind of non-deterministic or stochastic evolution related to the reduction of the state during measurement on the other side. And that was really a big riddle of pioneer quantum mechanics that even concerned philosophers of science for to some amount. And later in this lecture, we can see that, in fact, there is no problem at all, namely using algebraic quantum mechanics. Well, so far we have only considered these pure states, which are given as superposition states and described by vectors in the Hilbert space. But then it's also important to look how an open quantum system can be described in this formalism. And an open quantum system is a quantum system that is somehow interacting with its environment. And the classical, the paradigmatic example for that, for example, would be a thermal system. There is this, so to say, metaphorical use of a heat bath. I will come back to this idea later, that a thermodynamic system is weakly coupled to its environment, which can be seen as a heat bath. So only small amounts of energy are exchanged between the system and its environment. And then, of course, we have to consider this individual system as an open quantum system, which is weakly interacting with its environment. And here we are using these density matrices or these density operators. So always such a density operator, a linear combination, a convex linear combination of projectors is describing such an open quantum system. And now we see how can we compute the statistical expectation value of an arbitrary observable in such what is called a mixed state or an ensemble state. And that means that we have to compute the trace. So, of course, we have seen that these density operators must be of trace class. They must be normal operators leading to a convergent series of trace here. And we multiply this density operator with an arbitrary observable, take the trace of that. And of course, one requirement for this is that the product of a density operator with an arbitrary observable is of trace class again. And this refers already to an important algebraic property, that such a product of an observable with a trace class operator must be of trace class again, which is algebraically speaking, that must be an ideal. But I come back to this at a later point.
Sorry.
So now we can look how a pure state is described in the framework of density operators. And then we see we have this kind of linear combination, but all the coefficients except one are identically 0, and only one coefficient is exactly 1. And then we see the density matrix or the density operator, which is simply one projector. This is called an atomar projector. This now describes a pure state as well. And maybe I can try this computation, that this is in fact equivalent. So what we do have to compute is the expectation value of D in an observable A is the trace of E times A. The trace is the sum of all the matrix elements of A, where D is by definition given by this projector. And now you see the advantage of the Dirac notation once more. Here we have introduced this projector, which is given as a linear form, namely a Dirac bra, a Dirac ket times the Dirac bra. And this, because and now here, this is the projector, but now we can equally evaluate this one. This is simply 1. This is the scalar product of n times n. So we have now I made a mistake, unfortunately, when I'm doing that from scratch. So I have to use a different summation index here, unfortunately. Because I have already reserved the index n for the definition of this projector here. So then we have to sum up over m. And now you see this is not always 1, but it's given by the Kronecker delta. And these are all the scalar products between the different basis vectors n and m. But now you see from this sum over all the Kronecker deltas, only one term remains. And this is exactly this. And that was the definition of the expectation value in a pure state. We see that all these concepts are at least compatible to each other. Well, often in quantum theory, it is necessary to not only describe a single system, but to describe composed systems. And I have already mentioned the case of an open system is a system that is somehow coupled with its environment. So at least we have to describe a composite system of an open system in its environment. And the mathematical concept for describing composite systems is the tensor product. So it's possible to define the tensor product of Hilbert spaces for such compound systems. This tensor product of all the individual systems, of all the individual systems Hilbert spaces is the Hilbert space of a composite system. And using the Dirac notation, it is quite advantage to simply omit this tensor product symbol, because we can simply enumerate all the different states coming from the individual Hilbert spaces and put them all into one big cat symbol, and that's the description of a state of a composite system in the Dirac notation. But now it's interesting that we can, so to say, describe an open system as a system that is embedded into an environment. We can consider the global system comprised by the open system and the environment. And then we assume that this global system must be again considered as an isolated system. And therefore, it must be describable by a pure state. And now we get this description that the state of an open subsystem is obtained by what is called outtracing the pure state of the global system through an operation that you all know from statistics. It's called marginalization. That you can project a joint probability distribution to each of its sub contributions, and this is called outtracing here. So basically, we have a projector, so a pure state described by a density matrix, as I have told before. Then we trace out over all the component systems except of one, namely the one that we are interested in. And this gives us the density operator of the subsystem that we are going to describe as an open system. And here there are two possibilities now. When a marginalized pure state remains pure, so we assume that this is a pure state, this operation here describes the marginalization. When a marginalized pure state remains pure, then we say that the system is separable, which is something different than the separability of a Hilbert space, just as a remark. But if this is not the case, So when a marginalized pure state is not pure anymore, we call these states entangled states. So, and you all know probably a couple of days before, the Nobel Prize was awarded to three important physicists, an aspect, Seilinger and Clauser. And these are researchers who did the crucial experiments and theoretical contributions to entangled quantum systems. So entanglement is a crucial property of quantum systems in general, which means that they have an existence beyond space and time, so to say. You all know this, this idea, the original idea that was proposed by Einstein, Podolsky, and Rosen about entangled photons, or later it was talked about entangled spins. That a spin system is prepared, and then the spins are separated, and you are measuring a spin experiment in one place in the universe, and then you immediately know the state of the other spin at the other side of the universe. And of course, there is no interaction between the spins. They are simply entangled, and this entanglement is preserved even through the separation over space and time. Here's an example, namely again for the spin systems, which is important in the framework of quantum computation again. So when we talk about qubits, we have seen that we can assign to Hilbert space vectors to a qubit or to a spin system, namely to a spin down system. We have assigned this basis vector in the two-dimensional complex Hilbert space. And written as a qubit, we simply introduce the Dirac ket 0. This should be the bit 0 as a interpreted as a qubit. And likewise, for the spin up state, we have assigned this Hilbert space vector, which is now in the Dirac notation, state 1 in the ket. And so here again, you see the differences between the two notations. In spin algebra I'm using, I usually have to compute these vectors in their respective basis representations. So we have to use Hilbert space coordinates all the time, but in the Dirac representation, everything becomes purely symbolical, and we do not have to compute coordinates all the time. But then in the quantum computation framework, we can build tensor products of qubits. So what can be called a qubit would be such a state of 8 individual qubits, which becomes a state in the respective tensor product 8 times C2, which is C2 to 8, basically the Hilbert space C16. And then we can connect these state vectors with some logical gates, quantum gates, for example, and compute the corresponding interactions between these states and quantum computation. Perhaps maybe we have a break now, or
yeah, for 10 minutes, please. For 5 minutes, yeah.
Yeah, 5 minutes break. Is this okay?
Yes.
Okay. And I take my slide and this is exactly at this point I thought I would make another computation.
Peter, are you working with? Are you trying to do anything with quantum computations?
Yeah.
Are you? Yeah.
Not really, no.
No,
No.
not yet.
Only theoretically, so to say. So what we really do is that we try to apply these ideas, these basic concepts to artificial intelligence,
Okay.
cognitive systems. And I will give you examples for this as well. But I don't work with quantum hardware or something
okay,
like
yeah.
that. Not but in fact, what I have told you yesterday in this huge 4 billion project in Cottbus, there should be a facility for quantum.
Oh yeah,
computers.
they're going to put one.
Yeah.
Oh my God, that's amazing.
Yeah.
Because at the moment, what we have is that the leading people are essentially companies, right? So you have Google, IBM. In terms of academia, we don't see facilities on quantum hardware.
Yeah. No.
That's amazing thing.
Yeah, but I think
So researchers will have access to that, or just to a group of people.
No, I think there's something yeah. Yes, of course.
This is linear because it's likely.
Do you think it will, this hardware would be feasible in the future? I mean, they're toy stuff at the moment, but
No, to be honest, I mean, there are so many practical problems, coherence,
yeah.
that all the quantum systems necessarily interact yeah, but maybe I'm wrong. I don't know. You can never predict.
Yeah, you can never predict exactly.
technology.
Yeah, right.
Actually, all technology is actually magic.
It's true. Yeah. But apparently they have done some, right? So, I mean, it's a very simple chip, right? Apparently I heard IBM, Google.
Different approaches. Historically, I think the first approaches were to use really spin systems as quantum systems. But what I have learned now is that it seems to be more
When this kid is really
more promising to look at
So,
these Josephson junctions.
Oh, I heard of it. Yes, okay, yes, right.
Can be used as two ways.
Right.
I think that's nowadays
So
mainly is this kind of solid state.
You said
small.
solid state, right? Yes.
Because it's much easier.
So the current based on what, thin or on solid state? Based on solid state. Shall we start?
Yeah, okay.
Yeah. Yep. So this bit is going to work for the first part of the graph, and then to get the second part.
Shall we start? Sorry.
Yeah. Yeah. Yes. Yeah. Yes. Oops. 2 to the power of 8, not 16.
No, it's not 16 now.
I'm sorry.
Yeah.
I'm sorry. Oh, what a bad way. We always say mathematics is the art for avoiding computation.
Yeah.
Yeah, I had to check twice.
I'm
The number was a bit too low.
I'm so sorry. Okay. Okay, shall we continue? Well, I just got the idea to demonstrate this computation of tensor products for a moment. So let us assume that we want to compute qubit state 0, 1. What does this mean? Of course, this means 0, tensor 1. And now we have to go back to the Hilbert space coordinate representation, which means that we have to take the state that one and that one. And now the crucial point is, how do we compute such tensor products? And of course, there's a very simple rule that the tensor product is given by vector in a higher dimensional space, simply by taking the elements of the first vector as scalar multipliers in computing the products with this vector here. You see? And then, of course, we get 0, 0 and 1, 0. And this is the corresponding tensor product in this representation here. And the same can be done, of course, for the spin operators, for the Pauli matrices, for example. So what is necessary for computing such a quantum gate or for constructing such a quantum gate. And by the way, if you don't realize that here, I made a crucial mistake. 2 to the power of 8 is, of course, not 16. I'm very sorry about this mistake. Okay, so and of course the matrices, the spin matrices, can be employed in the same way. They have to act then on, for example, here 4-dimensional vectors. You have to couple the corresponding spin matrices in an equal way, and that's the way. This is basically the essence of quantum computation. But in the next slide, I have presented another example, namely from quantum mechanics properly. And this is also quite instructive example where we use this so-called wave function representation. So that's basically called Schrödinger representation. And here we are looking at a particle that is captured in a box. So it's called the particle in the box model. The box has a finite size, and the particle has only 1 degree of freedom, so it can only move along one direction. It does not have 3-dimensional space available, but in the simple mathematical model, it's only moving along one line. It bounces into the box, it gets reflected, and so on and so on. And how can we treat this in the formalism of quantum mechanics? Well, even if this system has only 1 degree of freedom, it is only able to move in one direction in 3-dimensional space, we have to deal with an infinite dimensional Hilbert space. And the Hilbert space is now given by the Schrödinger wave functions, and we are using a particular basis function here. This is given by these normalized trigonometric functions. Here you see there is a quantization condition involved, that the sine waves are restricted to certain quantum numbers, which is the parameter n here. And you see the Hilbert space that we are using here is the space of square integrable functions over the interval 0 to L, where L is the size of the box, where L is the diameter of the box. This is the basic function system that we are using here. And then there are crucially two important operators. One is the position operator, describing the measurement of the position. And its impact on a wave function is essentially that the wave function is multiplied with the actually measured position. And in mechanics, we also must be able to measure the velocity of the particle, or physically speaking, the momentum. And interestingly, the momentum operator acting on a wave function is given by a differential operator here, which is minus the imaginary unit, the Planck's action of quantum of action, and here the derivative of the wave function towards x. And then, of course, in order to look at the time evolution of the system, and what is plotted here are basically, because the wave functions are in generally complex functions, they always involve a time-dependent complex phase here. And what is plotted here, and this is an animation taken from Wikipedia again, in blue is the real component, the real part, and in red is the imaginary part. And these are the first eigenfunctions of this representation here. N equals 0, n equals 1, n equals 3, or 2. No, probably 1, 2, 3. Yeah, of course, 0 wouldn't be an eigenfunction here. N is 1, 2, 3. And these are some superposition states of these eigenfunctions here. And the dynamics is described by the Hamiltonian, the energy operator, and these eigenfunctions, or these basis functions here, have exactly the property that they are eigenfunctions of the Hamiltonian. So therefore, it's important, if you are measuring energy, you apply the Hamiltonian operator to a state, and you get an energy eigenvalue as a measurement result of the energy of the system. And again, what we can study in some detail here, but yeah, I will postpone this to some later point. So this was one simple example of standard or pioneer quantum theory. Now, where we have looked at an infinite dimensional Hilbert space presenting the Schrödinger representation of such a particle in a box. But what's important, of course, here was again, when we restrict the particle to a box, we have a particular Hilbert space, and we can deal with all these eigenfunctions. Just a question that I would like to address here. What happens if we make the box tending to infinity? Then these quantum numbers become bigger and bigger. We get more and more eigenstates allowed here. And finally, if we take the free particle, which is not restricted to a certain boundary, we can still use the formalism. We can still calculate these operators here. But interestingly, we have to leave this Hilbert space, because the free particle is described by all complex exponentials, so by all harmonic functions, and they do not belong to a Hilbert space anymore. Yeah. You can use some technical tricks, of course, but this is basically a problem of this pioneer quantum mechanics, that it's not possible to describe in this given framework without technical tricks, so to say, unbounded free particles. So the problem here is what is called that these operators here become unbounded. So the eigenvalues of these operators have no limits anymore, and therefore these operators cannot be normalized. And this is a technical problem. It was not a problem for physicists all the time, but when mathematicians began to study these problems, they realized that one has to teach the physicists how to make it forward. So, and therefore, this so-called pioneer quantum theory involves some peculiarities. And these are, first of all, that the pure Hilbert space states only describe isolated systems. But from a more philosophical point of view, what is an isolated system? An isolated system is a system that cannot be observed. So can we do physics about isolated systems? No, we cannot. It doesn't make any sense. You cannot make a measurement on an isolated system because measurement always needs to bring a system into interaction with the measurement device. And then it's not isolated anymore. So that was my point. Isolated systems are principally not observable. Then we have already mentioned this problem that measurement has been, so to say, ad hoc included into the formalism by von Neumann's projection postulate, saying that during the interaction of the system with its environment or with the measurement device, the system decides to jump into an eigenstate of the observable. And then we can only say with which probability the system actually does this jump into an eigenstate. And we don't have any deterministic theory how the system really gets into this eigenstate. This is called the measurement problem of quantum mechanics. This was really a puzzle for physicists and even more for philosophers of science all the time. Another problem that became apparent during the development of this formalism is we are living in a classical world. How can we describe the emergence of classical properties from this formalism, which does not allow classical properties at all? We don't know. Pioneer quantum mechanics is not able to describe classical systems. Of course, in the textbooks, you will find something like in the classical limit, let us tend Planck's constant of action towards zero. But this is not feasible. You can use a different measurement system, of course, where the Planck's action constant of action can assume different values. So you can use a unit system where it takes the value 1, of course, but you can never introduce a system where it takes actually the value 0. And even as a limit, it's not possible at all. Then it became apparent that pioneer quantum theory is not able to describe irreversibility. Because what we have seen is that time evolution is always described by the Schrödinger equation, and mathematically, Schrödinger equation corresponds to unitary evolution. And unitary evolution always preserves distances and projections in the Hilbert space. And therefore, there's no, so everything is reversible in a unitary evolution. And it's not possible to describe the emergence of irreversibility. And what we have discussed before, bless you, was that performing a measurement needs some kind of irreversibility, because the measurement device must have some relaxation dynamics in order to get into equilibrium. We need irreversibility to describe measurement. And then, of course, there are conceptual problems, for example, spatially extended systems, as they are considered in quantum field theory. One of these problems is that we have seen that states can be entangled. And that means states have an existence beyond time and space. But on the other hand, in particular in relativistic quantum field theory, you request that the system should be compatible with special relativity. How can we solve that question? And of course, this question has been solved, namely in the framework of algebraic quantum field theory. And of course, if we are applying the ideas of pioneer quantum mechanics to thermodynamical systems, we at least conceptually have to consider infinite systems with an infinite number of degrees of freedom. What I've mentioned before, coupling a thermodynamic system to its environment, and the environment is essentially the entire universe. And as long as the environment also contains the radiation field, we have to deal with an infinite number of degrees of freedom in order to approach problems of thermodynamics. So these are the peculiarities of pioneer quantum theory. And of course, there is some philosophical problem involved, where I always like to refer to Plato's Republic. And this is an image, a picture taken from an issue of the Neue Zürcher Zeitung, which I like very much. So you probably know that Plato is describing in his cave metaphor that people are captured in a cave, so they are bounded on a wall, and behind the wall some other people are moving things or objects along, and these objects are enlightened by fire here, and they throw shadows on the wall, and the people here, they are only able to look at the shadows. They don't recognize the proper things here. And so that leads to an important philosophical distinction, so the cave allegory, namely between the distinction between ontology as things as they are, independent from the observation. So is there a real world, and how does this real world look like? In Platon's philosophy, it's related to the ideas, and today one would probably say it's more related to structure. And then there's epistemology, relating to knowledge, which is related to appearances, or quite importantly for our days is meaning, that the objects as they are, they don't have any meaning for us observers, but only because we are observers, the objects assume meaning. And in the following, I would like to address a connection of this entire framework of algebraic quantum theory to this basic distinction between ontology and epistemology. So, in order to motivate the next step, which becomes more and more abstract now, it makes sense to look at the classical dynamic system, like the spring pendulum here. So in a spring pendulum, we of course prepare such an experiment that the mass is connected to a spring, and if we make an elongation of the mass, the spring is going to oscillate. So this is the apparent behavior, and in the first step, in order to provide a mathematical picture of that, we are looking at a so-called state. And then in mechanics, of course, we know that the state comprises position and momentum. So we embed the state into a two-dimensional state space, or what we like here to say is into a phase space. We have the position variable as one axis, and we have the velocity or the momentum variable as another axis. And then we see this movement of the pendulum corresponds to a circular dynamics in this classical phase space. And then, of course, the behavior in the space direction alone is regained as simply a projection of the circular motion. So this is the first level of description for a classical dynamical system. Well, then we develop appropriate mathematics for that. This mathematics says that we are describing a classical system by this phase space, which I call X now, and by a mapping, I call it phi for flow, which is a two-parameter mapping, taking one real number as the first argument and a state in the phase space as the second argument, and mapping this back to the state space. And what we actually do here is that the first argument, the parameter here, taken from the real numbers, is time. And then, of course, we can map any point in time to phi of t, given a so-called initial condition as our first state. And then we can iterate this mapping for all times, and then we get a so-called trajectory. And this circular motion here is a trajectory of the system in phase space. Well, one usually makes some topological assumptions about the phase space. It should at least be a locally compact Hausdorff space, or if the system is captured to a finite volume, as the particle in the box we have seen before, then the Hausdorff space is assumed to be actually compact. And interestingly, we can derive an important algebraic property for this flow, namely that we have a so-called dynamic semigroup, at least a semigroup. That means applying, the battery is going away, applying the flow to the sum of two times means applying the flow to one of the time first, and then applying, so we compute the point, the state along a trajectory given in the initial state x, spanning time s, and then we use the corresponding state that has evolved during the time s as an initial state for computing the state after time t afterwards. And this, of course, must be the same as computing s plus t applied to the initial state x. And now, of course, because the real numbers have a group structure, we can replace the sum here as the difference. We can compute inverses. So the flow must be reversible in that case. And therefore, one considers a group, a dynamic group. But it is also possible to get rid of invertibility here at that point. And now the battery is completely lost. What can we do?
Maybe you have to do it by hand, just pointing by hand, I don't know.
Okay.
I'll ask I would say.
Okay. Okay. I will try. Yeah. And so for that reason, if we get rid of the reversibility here, we would speak about a dynamic semigroup, where not every element in the group must possess its corresponding inverse. So, and here you see another important dynamical system. So when we are looking at chaotic dynamics, this is just an image of the Lorentz attractor here. And interestingly, this kind of dynamics now relates to measure theory, what we have discussed before. So for such a system, when we have a strange attractor, it is possible to look at such a measure function. So a function that assigns a number to a set, a probability, for example, that the system already belongs to a given set. And here, so for example, if we look at a subset of the Lorentz attractor, the measure should have this invariance property that the, so to say, another possibility would be not to look at probabilities, but to consider only the volume of such a set in phase space. And then if we have an invariant measure, it says that the volume of this of some set A does not change over time during the dynamics according to this flow. Then I have introduced here, thinking about proper notions, and it came to my mind that another important property of such dynamical, nonlinear dynamical systems is called structural stability. That the flow of the system should be stable against small perturbations in its parameter space. So sometimes we know that the flow depends on certain parameters, bifurcation parameters, for example. And if the system is stable against small changes of the parameter space, we have this property that the original flow can be topologically conjugated to a perturbed flow. And that means here we have to apply a homeomorphism, so the continuous map with continuous inverse. And I like to introduce the concept of resilience here, because it essentially means structural stability. And then finally, one introduces this so-called mixing property. That means that the probability, so to say, of an intersection of A and the time rate of another subset B should decorrelate. So here you see we are taking the probability of the conjunction, and here we take the conjunction of the probability, so to say. This is basically a decorrelation condition. In statistics, you always use the idea of statistical independence. And two random variables are called statistically independent if the joint probabilities factorize in that way. And this is, so to say, the idea of statistical independence applied to a dynamical system, which is called mixing the mixing property. Another important description or distinction, which brings us back to this ontological epistemic distinction here, is that dynamical systems can be described at different levels of abstraction, so to say. So what we have seen with this pendulum, for example, was that we are looking at the state in the phase space, and this is that can be called a microstate. But on the other hand, it makes sense to look at probability distributions over the phase space, classical probability distributions. So here, for example, a two-dimensional Gaussian. And then we can look at the supports of these distributions, and then we have to identify the essential support of such a distribution with a set in the phase space. And these sets that could be considered as macrostates. So we have, so to say, on the ontological side, the evolution of microstates. Ontological, because this describes how the system really is. But on the other hand, the macrostate simply describes our knowledge about the system that we have. And this knowledge is described or is expressed by means of these probability distributions. So this was just the first motivation. These dynamical systems, nonlinear dynamical systems, measures on the phase space. And now I make the next step towards the algebraic approach. So as before, when we were discussing the structure of pioneer quantum mechanics, I give you the very basic ingredients of these new concepts. So first of all, we simply look at a vector space. We look at the vector space over some number field, which could be the complex numbers or the real numbers. And then we introduce a binary function on the Cartesian product of this vector space to the vector space. And we say this defines a product if, first of all, we have associativity. Then we claim that we have distributivity in both arguments. So the linear combination, we are in a vector space, so everything here is a linear combination. Scalar factor times A plus the scalar factor times B times C should be the same as scalar A times AC plus B times BC. And then, of course, we are also requesting the second kind of distributive law, where for all capital elements in the algebra in the vector space and all small numbers in the number field. And this essentially defines an algebra. So an algebra is a vector space with an external product, mapping two elements of the vector space onto a new element, and that's called the product of these elements. We call an algebra a commutative or abelian algebra if all the elements in this vector space commute with each other. And of course, we have already seen in quantum theory, these algebras will not be abelian. And we call an algebra unital if it contains a unit element that commutes with every other element. And just as a note, not every algebra must be unital, but fortunately, every algebra can be embedded into a larger algebra that contains such a unit. And therefore, in the next slides, I will always look at such unital algebras. Well, then we introduce some topological structure, and this leads to the concept of the Banach algebras. So remember that a completed normed vector space was a Banach space, and now we can extend the Banach space towards the Banach algebra simply by introducing this relation, how the norm behaves with respect to the algebra pose. And here we state simply that the norm of the product of two elements could be smaller or equal than the product of the norms of the two elements. And this norms, of course, introduces a uniform topology on the algebra. And if the space is again completed with respect to this induced norm, we talk about a Banach algebra. Then we introduce another concept, namely we introduce a mapping, which is called star. This mapping has the property to being an involution, namely in the case that an element of the algebra is mapped onto another element, called a star, if we have these axioms fulfilled. So taking the involution of R and taking the involution again reproduces the element A. Then we have some linearity assumptions that the sum of two elements involved in involuted should be the involution of A plus the involution of B. Interestingly, for the product, we have to exchange the two elements in the involution. And if we multiply an algebra element with a complex number, we have to take the complex conjugate of that number in order to compute the involution. So here I already assume that our underlying number field should be the complex number. And of course, you already realize that these are the properties that really hold for complex conjugate in the complex number field. And this is simply the idea to generalize the properties of the complex number fields to more abstract structures. And then we are talking about Banach star algebras. That is a Banach algebra having this or possessing this involution operation. So, and finally, we define a C star algebra, and this so-called C star property holds relating the involution and the algebra product and the norm together. So that means basically that A star times A, taking the norm of that, should be simply the squared norm of A. Now I'm back. Okay. And now it makes sense to discuss several examples. First of all these axioms have been chosen in such a way that we get almost the same properties as in the complex number fields, except probably the commutativity. And this will exactly be the reason why we have introduced this concept of a star algebra, because we want to have as much the properties of the complex number fields except commutativity. So, of course, the complex number field is an example for such a concrete and commutative C star algebra, but now over the real numbers. The proof, because first of all, the complex number field is isomorphic to R square, to the Gaussian number plane. Then, of course, we know that the Gaussian number plane is a two-dimensional real vector space, and it is, of course, a Banach space because it's complete. And then we can identify the zero of the complex numbers with the pair 0, 0, the one of the complex numbers with the pair 1, 0, the imaginary unit with the pair 0, 1, and then we additionally introduce the standard assumption that I square should be -1. And now you see, after having made these identifications, we can simply compute the modulus of a number, which is the square root of the complex conjugate times the original number. And the complex conjugate is introduced as this kind of involution here. And then, of course, everything is fulfilled. We have a C star algebra. The second example, a bit more complicated. Interestingly, the space of continuous complex valued functions over some n-dimensional hypercube. I'm using this hypercube here, so to say, more for didactical reasons. I will come back to this example many times. Let us look at a phase space which is simply given by this kind of hypercube. All the real numbers between 0 and 1, and then extended to some Cartesian product here in belonging to Rn. And now we look at the complex, at the continuous functions over this phase space, and this gives us again another commutative or abelian C star algebra over the complex numbers. And here's again a sketch of a proof for some functions f, here, and h that are continuous over the hypercube x. Define, of course, the sum of two functions in the argument is the sum of the values in the argument. The scalar multiple of a function is simply the pointwise multiple of the functions. And then, of course, the algebra product is given by this product here. Then we have to introduce the norm. And at least for this bounded phase space, we can simply say that the norm of a function is the maximum of the modulus of the function over all the values in the hypercube. Of course, in a more general setting, when I allow for example, for the entire Rn here, we have to replace the maximum by the supremum. This is only a technical difference. And finally, because we are dealing with complex functions over the hypercube that assume values in the complex number field, we can introduce the involution simply as a complex conjugate at a particular value. We have proven that this is a C star algebra. And here's my first application. And so basically, I have to say now that I will present many applications, but all the time I will scatter them throughout my lecture. So I have examples, I have applications, and maybe at some point at the end of the lecture, we have to discuss applications in more detail. But so far, I would like to scatter applications throughout the sessions here. And this is actually the reason why I have chosen the n-dimensional hypercube, because this could describe the activation of a neural network. If we are going to describe the activation of a neuron by its spike rate, we can normalize the spike rate to a number between 0 and 1, which is often done in computational neuroscience, because the spike rate should reflect the spiking probability of a neuron, and then it must be a number between 0 and 1. And if the activity of the spike probability of a single neuron is the number between 0 and 1, the activity of an entire network consisting of n neurons is a vector in the n-dimensional hypercube. So here you see the reason for my selection, taking the n-dimensional hypercube as a particular phase space. Now it makes sense to look at the topology induced by this state space of this algebra. As I have already said, we are using the maximum norm of the functions that are assumed for all elements in the complex in the n-dimensional hypercube. And with respect to this uniform topology, we can define uniform convergence of function series, such as the Taylor series or the exponential function in this algebra C of x, in the algebra of continuous functions over x. And here's an example, namely how we can approximate a signed function over the interval from -pi to +pi by polynomials. And here you see the corresponding expression. These are the first terms of the Taylor series of the sine function. And you see again that for some order of the approximation, you see, of course, in the first order, the linear function is only a tangent on the sine function. But for the second order, you see that this is this polynomial, and it remains in the given stripe, so in an epsilon interval in this function space, for some time. And if we increase the order of the approximation more and more, all the points are captured within the stripe, and eventually they are leaving the stripe, because of course we only deal with polynomials and not this sine function. But eventually, you see, taking this uniform norm in the function space, we are able to describe uniform convergence of these function series. The convergence of the series of polynomials towards the sine function. And as if you remember our discussion yesterday, we have distinguished between strong topologies and weak topologies. This is an example for a strong topology, which gives rise to uniform convergence. But now, another example, namely the set of bounded linear operators, I call it B of H, over a complex Hilbert space, is an example for a non-commutative concrete C-star algebra over the complex number field. And of course, here's kind of sketch of the proof. We can define the sum of two operators by applying the operator to a state and then computing the sum of the states. And the sum of states is, of course, very defined because the states are members of the Hilbert space, which is a vector space where the sum is very defined. Then we can define the multiple of an operator. And of course, this extends to a multiple of a vector in the Hilbert space. And interestingly, of course, the product of two operators is now defined as the composition product of the two operators, because the operators, of course, are maps, are homomorphisms in the Hilbert space, and they can concatenate in that sense.
Sorry, Peter, can in the C-star algebra shouldn't be B? Shouldn't the product be the opposite B times A?
No.
No.
No. I say A after B, and this is exactly A after B.
But one of the properties in the C-star algebra in your previous slide
This
was the opposite.
This relates to the involution.
Ah.
And I don't compute the involution at that point. That's simply to define the algebraic structure.
Mm-hmm.
But then, of course, maybe we can do this afterwards. We have to check, of course, whether there are all the other properties being valid. Yes. And then we define the norm of an operator as now this primum norm that we compute the images and the operator applied to any state. We take the norm of the state because we are in Banach space. The Hilbert space is Banach space with norm, and then we normalize by the norm of the states. And of course, here the norm in the Hilbert space has been defined by the square root of the scalar product of the space of the state with itself. And finally, and this is now the crucial point, we can define the involution applying to a ket vector, which is basically the same as applying a bra vector. So the transposed state vector applied to the original operator. And from that here, you will see immediately that we get the C-star properties. And so now we have really found an example, which we have discussed all the time before, that the operators in the Hilbert space give us an example for such a C-star algebra. But there's one important point, that we have to restrict our operators to the bounded operators on the Hilbert space. And therefore, all the examples that I have presented before, the particle in the box or the spin algebra and so on, they are examples for such operators, but the free particle cannot be described in this framework. The free particle is really a peculiarity of the algebraic approach. And we have to look later how we can describe a free particle in this framework. What's the time saying?
Yeah, 2 minutes to go, but you still have 5 or so, depending on, because we started late.
So
it's up to you.
I can make this the next application. So this is simply for illustration how the Schrödinger representation is applied to atomic physics. So these are the orbital functions in a hydrogen atom. You see here we have a three-dimensional wave function, which is has a spherical shape in the ground state. Then we have these p orbitals and so on and so on. But that's just an illustration for the point how this relates to pioneer quantum theory. In pioneer quantum theory, and this is basically the work by John von Neumann, all bounded linear operators over a Hilbert space are considered as valid observables. Interestingly, this has an enormous consequence. Namely, it relates to what is called von Neumann's irreducibility postulate. And this postulate made by von Neumann in his mathematical codification of quantum mechanics in 1932. This was really the reason why quantum mechanics is not able to describe classical properties. If we simply relax this claim here, if we simply say, well, let us look at the C-star algebra, which is not identical with the algebra of all bounded observables, then we will immediately see that classical properties can emerge. That's quite interesting. But this, I think it's a nice point to interrupt for today. So let us conclude the session. Or if you have any questions, still can discuss. But I will continue tomorrow.
Thank you.
You're welcome.
Feel free to ask questions, yes. Johnny, maybe? No. No, everyone is satisfied.
Great.
Peter, I just wanted to ask one question, but in fact, and again, this is my ignorance in quantum system. There is this distinction between ontology and epistemology that you define, but we as observers, when we prepare the experiment, aren't we putting an expectation already in the preparation of what we want to observe? So how is this accounted in all this formalism?
This refers to epistemology.
But we are the one who are preparing the experiment, right? So we are deciding what to put in.
This is actually one of the last slides in this lecture when I talk about contextual emergence. That it's always the case that observers define what is considered as relevant for their investigation. And this imposes a particular context, and this really defines the distinction between epistemology and ontology. We'll come back to this.
Okay, so that's interesting.
Of course, it's interesting. Yeah.
So the act of preparation is actually very okay.
You always have some goals when studying this system. These goals are reflected in your mathematical apparatus, so to say.
Right. But is there a way to have say a set of experiments, a set of preparation whereby you somehow map between all these preparations somehow? I don't know. Like for instance, in one experiment you decide one particular type of measurement.
Yeah, of course. This is.
And then there are ways to.
This is really the starting point of the entire development of quantum theory, because we have this particle wave duality. What is an electron? Is an electron a wave or is an electron a particle?
Maybe it's not neither.
Maybe neither. So that would be the ontological point of view, that an electron is as it is, nothing of that. But if epistemologically, it can be both of the two, depending on your perspective. And this I have shown yesterday, that the lattice structures of quantum theory are in such a way that they are not Boolean, because a Boolean description which always reduces to one particular perspective or one ontological stance, so to say. And if you have perspectivity, you can decide whether I would like to observe the electron as a particle or like a particle or more like a wave.
But there could be a third experiment whereby you show that there's something more.
Exactly, of course. And exactly these experiments have been conducted in the meantime. So you probably know these so-called double slit experiments, where you have the control to observe the behavior of the particle either as of the object either as a particle or as a wave, depending on whether you open one slit or both slits simultaneously. And then people really designed crazy experiments where you can try to observe the particle or the object even after it has passed the double slit. And then it is possible to superimpose wave and particle properties to any extent. And
I did not know about this yet.
it's crazy.